A lot of extremely interesting stuff. Yeah, thank you very much for speaking with us today.
Okay. This one, yeah. This one.
It just keeps causing problems.
Problem is no good.
I'm sorry. You want the laptop back? Sure, I'll take it.
All right. So first of all, apologies to the YouTube folks who are here. Listening to this maybe a little bit of the second time. I always try to insert a little bit more. So I've been giving this talk in the last couple months, like maybe 2 or 3 months since KDD. What I aim to do is try to see if I can be provocative and change your minds a little bit. And maybe even possibly make a few of you multi-millionaires. And in fact, I believe there's, mark my words, I think 7 years from now, there will be $1 billion opportunity in the talk that I'm talking about today. So if any of you decide to quit your jobs or quit your school or whatever and start a company, please get in touch with me. I might just actually want to invest. Okay? In fact, if there's time and someone asks me, I'll give you a $100 million company idea right after this. Okay? The reason for it is because I believe Discovery Systems is about to go through a giant change. And in fact, I believe this entire conference ought to be changing in a different direction. In fact, just a few months ago, I emailed the steering committee of the RecSys conference and asked them, what their plans were for the future. And I hope you will agree with me by the end of 45 minutes that what I'm saying is true and that you would change the way that you do things going forward. Okay? I'm going to sit this down and see if it works well. Is this okay? Everyone can hear me? Okay, so many of you may or may not know that for a very long time, I was actually trained as an HCI researcher. And the history behind this, I will in fact tell you a little bit more in the middle of this talk. But if you think about what we typically talk about in conferences like KDD or RecSys, we're typically talking about these two kinds of systems. Recommendation on one side and search on the other. And recommendation systems is very interesting because, in fact, I have these debates with Lexi and with Christos and other people who said, look, RecSys has allowed me to use this very unfriendly term, but degenerated all the way to the point where it's a single feedback of just flick. I mean, think Tinder, right? Or Shorts. This is what we experience and what users want sub-second recommendation response. And that is a very intuitive kind of processing that they're doing. When they're looking at a thumbnail, they make instantaneous decisions whether they're going to actually watch that little clip on TikTok or YouTube Shorts or whatever, right? On the other hand, when they're really looking for something, I hope all of you did this, except our PhD student who graduated from here, you must have searched on Bari, Italy in YouTube. And when you searched, you looked through many tourist, blogs and looked to see which one might be the most interesting to introduce the town. In fact, maybe even you did it. Right? And then you're spending a lot of time thinking through each segment, parsing the results, making decisions. In cognitive science, this is what we call system 2 processing. We do very deliberate decisions about what is the next thing I'm going to pay attention to. In fact, you made a very deliberate decision to come here and listen to this talk. And you're engaged with your brain to hear this talk. You're not just tender, oh, it is not interesting, click, right? That's not how it works. So how do we actually implement both? With ranking functions. In fact, we had a Facebook talk just in the previous session, all about just how do we build better ranking functions. Now, why do we do ranking functions, by the way? Well, a ranking function is fundamentally about a list, yeah? In fact, search engine, a lot of people just said it's just a list of 1 through 10, right? 10 blue links. That's all there is to it. Why do we have a ranked list? Because humans process information sequentially, right? We read and we process information sequentially. So that's why we implement ranking function. That's why it's HCI. It's connected to how users process information. That's the commonality between search systems and recommender systems. They're both sequential processing information systems. So you implement them with ranking function. In fact, to tell you a little bit of the secret, I can't tell you what the neural architecture is, but inside of Google, all of search, all of ads, all of YouTube, both search and recommendation, in most of the major systems that govern more than $200 billion of revenue, probably 300, it's all implemented by a single style of neural network. That's it. It's not even like lots of different, like MOE here and transformer over there. No, they're all currently implemented by a single type of neural architecture. That's it, because you're implementing a ranking function. So what user discovery fundamentally has been about is using lists as the common user interface. Now, if we're using a list, a ranked list, as the common user interface, I hope you'll agree with me that me and my team, and everybody here, has done a lot of work doing this over the last 10, 15 years. In fact, I will go through a little bit of history behind how we arrived at this point in time, in history. In my team alone, we have implemented more than 950 improvements. And of these, probably more than 600 or so, probably 400 to 600 or so are in YouTube, because we use it as a research platform. But we also do a lot of work with ads that we don't typically talk about outside of my team, outside of the internal Google literature. But we have contributed to more than $9 billion in annual revenue, not total revenue, annual revenue. So I always joke with my colleague Lee Chan, who should be here in the audience somewhere. Lee Chan, over there, that he and I, when we started this research group, if we had an agreement with Google to only take 0.01% of the revenue that we have earned, I would not be giving this talk. I'd be lying on the beach somewhere in Bali right now, with a yacht that had sailed through the harbor, right? But I didn't make that deal, so I'm here to tell you that maybe you should start thinking about the deal that you should be making going into the future. So how is the world going to change? How is the world going to change? The first thing I'm going to tell you is that I believe that we're on the cusp of unifying all the recommendation and search systems into a single architecture. Okay? And how it's going to happen. The second thing I'm going to tell you is that the ranked list might be coming to an end. Possibly. We don't know for sure, but it might be coming to an end. Okay? So let's start out with the first story. On the recommendation problem, it can't be more simple than this, right? I do this every single day. I have a giant book bag that I carry to the office all the time. And I reach in and I'm looking for something and I go like this until I find something. I'm usually looking for my sunglasses case. I reach in and pull it out. That's the recommendation problem. It's literally just reach into a bag and pull out something. Now, sometimes you have RecSys problem, which is like a couple of billion items in there, so you might be searching for a while. Other times, it's only 10 or 20, right? So it's not so bad. When this problem was first started in 1992 or so, there was some paper of the place that I actually worked at called Xerox PARC, of a paper called the Information Tapestry. That might be considered the first recommendation systems paper, but the second paper in this space is much more well known. And I was a young graduate student at the time. The lead researcher at the time was my PhD advisor, John Riedel. He came to me in 1992 and said, we got this incredible idea You know how you have a lot of like net news? How many people remember net news? Do people even read a group lens paper anymore, by the way? So back in the days, in 1994, almost before the days of graphical user interface, okay, we had a terminal, text terminal, for reading group messages between people. This was a generalization of email lists. And there were so many messages by the time in 1992 that we couldn't read them all. And so John Riedel decided to start a project with Paul Resnick at MIT of a project called GroupLens. And there was all these ideas about Better Bit Business Bureau, and the user were going to contribute all these ratings, not just swipes, but 1, 2, 3, 4, 5. Remember those ratings? We were going to do that and build something called a personalized recommendation system. And the idea was to use Pearson correlation to do this. And in 1992, when they were building this system, I told John Riedel, my advisor, even though he was my advisor, even though I'm Asian, I'm supposed to listen to everything my teacher says to me. I said, John, that is the stupidest possible idea I've ever heard. You know why, John? Because what people do is different from what they will say is actually their taste. Right? They will pay so much attention on net news on sex and porn and blah, 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 but they'll rate it low, even though that's what they pay attention. So I said, this is a dumb idea, I'm not going to work on this. Plus, you're using Pearson correlation. That's an idea from the 1900s. Come on. I mean, this algorithm couldn't be simpler. So there's nothing here. As you can see, if you look it up right now on Google, my name is not on that paper. It has more than, I don't know, 20,000 citations or something. And I missed the opportunity to be on one of the most iconic paper in probably all recommender system history because of that single mistake. Don't make that mistake going forward based on the talk. Right? Now, John Riedel passed away in 2013 from skin cancer. In fact, just as he was about to, when he found out that he had skin cancer, he was planning on interning. He was planning on spending some time in my research group at Google, working on a problem I'm about to describe to you. Now, what's the moral of the story? Please wear your sunscreen. It looks like Italy is it's quite nice with the sun, so please wear your sunscreen. But let me dedicate the next section of my talk to John's contribution to this field. For many of you who have been here since the early days of RecSys will remember him as being this very friendly and who's willing to talk to all the students and everybody about the recommendation problem. But John, in some ways, because of my influence, ended up working on Wikipedia and other social contribution systems, and didn't really work on the next stage, in my personal opinion, of the recommendation problem, which was dealing with contextualization. So it turns out, and many of my colleagues like Li Wei and others who are here know about this problem much better than John did, even in 2013. Which was, it turns out, you wake up in the morning and you're using your phone. You don't want the 10-minute recommendation from you, right? You want the 30-second summary of what Trump said last night, right? That's what you care about. And because you're in between brushing your teeth and drinking your cup of coffee, and you need quick, move closer to system one kinds of experience. But if you open up your laptop, you type in your password, well, you must be sitting down, first of all. It's really difficult to type in your password on your laptop. So you're in front of your desktop, you're much more likely to be willing to watch a video of significant length. So context matters. What you recommend to user matters, right? We all know this by shopping, and they look at you up and down to make a decision on how much you're going to spend, right? All sales shopkeepers do this. Context matters. What you wear matters. So what's going on in this space is very interesting, is that once you start thinking about the recommendation problem, problem of building a ranking function. And since we're talking about ranking, let's just add one more thing into the middle of this, which is queries. Okay? Once we do this, you'll see why the neural architecture are exactly the same. Okay? Now, let's play a quick game. The YouTube folks and people from my team, I think there may be 10 or so of you in the audience, are not allowed to play in this game. Okay? But others who have not heard of this fun little game just now, you're eligible to participate. In fact, you know what? I have some stickers in my I literally did not prepare for this. Okay, so how many stickers do I have? I got 4. No, 5. That's literally all I have. Okay. So this is going to be a game where if y'all have the correct answer, you get a sticker. All right. So I am going to claim by the end of this talk, you will agree with me that this is the grand unified ranking function that we're going to be building in this conference and this community going forward. Okay? Again, for those of you who have listened to this talk, you're not eligible, and I know some of you are faces. So if you take this function and I get rid of some input features, like for example, these two, I take out the user and the context. What do we call that? Search. Oh, I think I heard somewhere here was the first one. Search. That's a search engine. Coming to a Google talk, of course you're going to get a search question, right? That's a search engine. What do you call this? Oh, I need to point right at the map. Okay. So, what do we call this? Oh man, that was getting really hard to discern who was first. So I think it's maybe up here. Hey, now it's going to get a little harder. What do you call this?
Recommendation.
Huh?
Recommendation.
Recommendation, that's correct. So then this one is easy. Yeah? Give you a Gemini stick. Wait, you already got one. Yeah. No. You tried to trick me. I recognize faces. Recommendations. In fact, a little bit off because it's personalized. So this is important because it could be contextualized versus personalized. What do you call this? And I want the accurate answer from this audience. Somewhere up there. Item to item collaborative filter. Now there's some controversies. There's some controversy as to exactly who was the first in inventing. Walking around a little too much. Now they want me to use the lavalier microphone. So there's some controversy as to who actually invented this first. In John Rito's lab, the Guru Saurabh was the first to publish it in an academic conference. So at least we can agree on that. So Greg Linden apparently also had done similar work around the same time at Amazon. So that's item-to-item collaborative filtering. What about this one? No? I haven't heard the correct answer yet. Huh? Training data? I heard a lot of co-star. I don't want the academic answer. Curation? No? Think like your grandma.
Similarity search?
No? Someone say random. No, I think that was Lee Chen. Getting close. Popular. You said popular. You said popular. Okay, it's getting very warm. What do you receive in your mailbox?
Advertisements.
Mass advertising, right? You drive down the highway, what you get is mass advertising. It's mass marketing. It's indiscriminate. In fact, it's like being in Florence and they're just passing you out flyers. How do they know you're hungry or not, right? They don't. They have no contextualization, no personalization. They're passing it to everybody. It's mass marketing. So I hope I've convinced you that if you are able to build this one single function, you can cover this entire space. In fact, I just told you that inside Google, that's exactly what has been happening. Everybody converging to exactly the same style of neural architecture. Now, as to why that particular neural architecture, it has to do with a lot of times, in fact, the current hardware that we have for serving, not necessarily for training. And so hardware and software, etc., what is actually efficient makes a big difference. Now, one way in which I lie is that in ads, there is the computation of bits. And that is very complicated. And generally speaking, in this conference, we don't talk about this. But in KDD, we do. And in some other conferences, we do. And bits are a little bit complicated in the sense that there's a second price auction, victory auction, you know all about that. And also the estimation of the advertiser's value in particular. It's a very tricky problem. I'm not going to go through any of those, but the retrieval is the same. You got this as constraints, and then you retrieve ads instead of items. It's still mostly the same function. I contend going forward, we should unify all this research. What happened was that we had SIG-IR. Now, SIG-IR was a separate conference because what methods did they use? At first, it was reverse posting lists. And then they used PageRank. And over time, because of neural network, everything started to converge. There's no reason to have these separate conferences anymore, in my personal opinion. KDD, SIG-IR, RecSys. Why are we separate? Only reason we're separate is because of historical reasons we have been separate. And the surfaces that we serve on are separate. But we're all implementing rank functions at this point. We do query understanding just as much as sometimes as SIG-IR, we just call it user understanding instead of query understanding. Now, if you think about this, this is pretty amazing. Why? Because the entire order and the structure of the entire internet is determined literally by these ranking functions. We're talking about $300 billion, $400, $500 billion worth of the entire market is governed by these ranking functions that everyone here is built. That's why you're here. That's why you spend thousands of dollars to come here, is to learn about the latest that's happening in how to construct these ranking functions. Now, let's talk about functions. Let's really talk about functions. Where ranking functions come from is that they came from functions. Now, computer scientists, for a long time, by the way, thought of themselves as a, how should I say it? They say that there's this term, a phrase that says, any area that is truly actually engineering discipline will call itself a science in order to be respected by the other scientists. So we call ourselves computer scientists, when in fact, we were just a branch of mathematics for a while. I'm happy to let you all know, as of last week, we can say physics and chemistry are subfields of computer science. Thank you very much. You have all arrived. Now, it turns out, what's really interesting about that is that actually, indeed, the order of the universe and the order that is defined by functions is what underlies the entire structure of nature. So that's the reason why they gave the Nobel Prize to AI in physics and AI in chemistry. Because what is happening is AI is helping people figure out the order of nature. Now, that's why functions matter, because functions determine order. In 2015, we were already able to do things like this. Put in an image, get it to categorize into the thing that that image is about, give you audio signals, it will automatically recognize what is said in the audio. In fact, this works so well now. I'm upset when I'm in a noisy bar and everybody is talking. In fact, I guarantee you that it's going to happen this week. Someone's going to be in a bar in Bari, pull out an Android phone, right? Talk to it and like call my mom because I want to show her what a great time I'm having. And when it doesn't recognize your voice, it's like, well, it's broken. Right? I can tell you that in 2010, when I started working at Google, how incredible that would have been because the error rate was 25%. At word level, the word error rate was 25%. Now you're upset when it doesn't recognize your voice correctly. That's pretty amazing. Right? In 2015, because of the seek-to-seek paper, we also know that you can put in a whole phrase, like, hello, how are you? I should have localized this to Italian. Instead of giving a French example. I need to apologize to the Italians in the room, at least to you. Can you actually tell us how do you say hello, how are you in Italian?
Very simple. Ciao, come stai?
Ciao is good enough, or buongiorno, and then
Come stai?
come stai. Is that more or less correct? Okay, so, it's pretty amazing when you think about it because by 2015, we were already using LSTM technology to translate by encoding the phrase and then decoding one word at a time. In 2015, I remember seeing this example and just being absolutely mind-blown. You can put in an image and ask it to caption it, and it will do it in perfect English, including the double L on traveling. And you use this traveling instead of travels, which is interesting in itself. And also, what's more remarkable to me at the time, as a near-native speaker of English, we typically say blue and yellow train, and we don't say yellow and blue train. And the reason for that is because of the color order in Western countries, is blue comes before yellow. So we say blue and yellow and not yellow and blue train. It's just one of those things about, being fluent in the language. Now, what's even more amazing is that, as I mentioned, that is generated token by token. So we all miss this. I know I can see across the faces today that you were all already thinking about computers in 2015. But you did not know that was the start of the generative AI revolution. And that was 8 years ago. If you had invested in the right stock in 2015, I guarantee you would have been multi-millionaire by now. It's absolutely incredible what had happened starting from 2015. In fact, most people forget this. Everyone cites the Google paper on transformers. But where it really started was the original paper on seek-to-seek learning. That paper had 3 authors. First author was Dharwadker, who became the chief scientist of OpenAI. The second author was Oriol Benyals, who is now the co-lead of Gemini at Google. And the third author is Khushhall, who now works in my group. Pretty amazing when you think about it, that I get to work with such amazing scientists who had this foresight in thinking about an entirely different way of creating recommendations, essentially. Now, we didn't actually stop there, not just from the transformer paper. In June of 2015, we already could foresee the construction of the conversational AI chatbot. In 2021, 2022, we published papers about how Lambda is built. And then very quickly in January of 2022, we also published the paper that I was a co-author of the chain of thought paper, which is now underlies some of the ideas behind instruction fine-tuning and a lot of synthetic data generation work that's happening in LLMs. Right. So I was on both of those papers because I recognized these trends too late. I was like, oh, by the time I realized, oh my gosh, what's going on with people like Quark in order to understand what was happening in this field. And then as soon as ChatGPT launched, we were able to launch Bard, which is now called Gemini. My team did it in less than 100 days. Why? Because we already have been working on all this technology at Google for more than 7 or 8 years. Right? So we saw the generative AI technology happening right in front of us. So what happened? What happened in 2015 was a very simple problem. If you were on the statistical machine translation team, you were very, very annoying for a very simple reason. At the time, I believe, Google said, we care about 40 languages around the world. Luckily, that means Italian is included. I think Italian is like number 7 or something like that, in terms of the most popular spoken. But think about this. If you were a statistical machine translation researcher that was working on phrase-based machine translation technology, how many models would you need to build for 40 languages? Translation between all 40 languages. How many? Oh, I still have one sticker.
780.
How many?
780.
780.
1600.
You will be correct if they're bidirectional. What if it's not bidirectional? I think, okay. Everyone now is shy about giving the correct answer. But 780, that just counted as being the closest to the correct answer. But otherwise, it would have been 40 times 39 divided by 2, right? Which would be 1560. Is that right? Yeah. So you're too far for me to walk up, so please, we'll give you this sticker again, right? So imagine you needed to create nearly 1,600 models just for the data center. And then you needed to create equivalent smaller versions of those models for your phone. And in all pairs. And you have to enable them for download. How many models? That's like another 3,200 models. And they have all to be updated in all the data centers around the world. You need a team of 100 people just to do all that, to make sure the data is correct, it was trained properly, tested correctly, quality controlled correctly, for every version of those models. I mean, it's just too much, right? So someone from my team, Wak and Ilya and Oriel, starts thinking, wait a minute, can we build one model? And the answer was yes. In NeurIPS 2014, they published a paper showing that you could get state-of-the-art translation capability between English and German using sequence-to-sequence learning with LSTMs. And then what happened in the next 2-3 years brought complete revolution to the language NLP space, especially to translation, but also to summarization, because they figured out they can use this method for summarization, because you simply have to tell it to generate shorter length translations. Amazing, amazing technology. What was so amazing about this was we didn't even realize this until several years later when we launched Bard. We had an example in Bard where we said, look at this code, figure out what the bug is, explain the bug to me in English, but write the comments in the fix in Korean. And it did it perfectly. And my brain literally just exploded when that happened. It fixed the bug, it explained what the bug was, and commented line by line in Korean. Right? So that was what we saw already more than 2 years ago. How do we still build ranking? Think about that. What has been happening, in my opinion, in this field a lot of times is that we're lagging behind in the revolution. We see what the language people are doing, what IR people are doing, then we try to borrow this technology and put it into our systems. We even celebrate it when that happens. I think that's crazy, right? We're the ones who are building systems that govern $300 to $500 billion worth of the industry. Why are we not the first ones to be innovating in this space? So why has that not happened? Let me tell you a little bit about Why? Okay? So first of all, the classic user item recommendation setup is looking like this, right? And we define a loss function to figure out what the missing values are. Now, the classic work in this space up until about 2007 was using some pretty simple technique, matrix factorization, SVDs, and things like that. And then we had some further factorization techniques. But for the most part, essentially we're trying to solve the problem by a linear regression. Now, why is there a linear regression? The idea is very simple. For this user, I'm trying to pick out one item that the user is interested in. And I'm going to pick out the next item after I think data comes from that one. That's how you build the rankings, right? One by one. Now, very importantly, that means that you're considering the entire row. That's why you need to think about negative sampling. Now, this is a concept that's very, very important for us to consider going forward. Now, with matrix factorization, it turns out that you're also considering which user you're going to pay attention to. That's why it's 2D. Now, I actually worked in the 2015, not realizing generative AI was happening. Worked on tensor factorization version of this, where we put the context as a third dimension. Turns out to be a terrible idea. I rescanned all those papers I published from 2015 to 2017 in this space. Terrible idea, because that was just too much negative sampling, basically. Now, the reason why that turned out to be a terrible idea was because of power law. It turns out that you have a power law on the item side and you have a power law on the user side. This event, I recommend something to Justin, I recommend something to Brad, I recommend something to WeChat, right? Each one of these are individual events, and when those events are correct, close to the truth, we call that unbiased. Now, it turns out, if you think about the problem as an individual event problem, it connects to physics. Because in the softmax, in dealing with the negative sampling in the row, this is the equation we use. In fact, I believe in the Facebook talk, they mentioned the softmax problem. So how do we do it? We take x times w, usually we do u and v, transpose, dot product, we raise the exponent, we divide it by a partition function. Now, that partition function, that softmax approach, is the same equation as the Boltzmann distribution. This is the same softmax that's in the transformer architecture in choosing the next word. So in fact, if I were to stop my sentences anywhere in the middle of my speech, you can complete it in your brain. And that process is a softmax process. That's how it's modeled in the transformer. Okay? Now, the person who discovered this, of course, was also a 19th century physicist. This is where I went wrong. I said, it's Pearson correlation. Oh, that's just Boltzmann distribution. Nothing. No. Turns out these connections between physics and partition function and the order of nature are deeply connected. A lot of people are kind of like, why are they giving a Nobel Prize to an AI scientist for physics? That's because they're not reductionists enough. They don't understand true science is in the order, in understanding order. And Boltzmann distribution, also used in the ideal gas law, for those of you who remember your college physics, describes the order of particles in a room when it reaches equilibrium. It's equilibrium mechanics. Equilibrium mechanics is about order of particles. Now, there's one person who got jibbed out of this. Sorry for the pun. Jibbed, sorry. Gibbs. Gibbs sampling, many of you who read machine learning literature also hear about Gibbs sampling. It's the same guy. This Gibbs. They all discovered the same thing, that this partition function is really, really important. It turns out, if you read our literature, is Xingyang here yet? In Michan's Xingyang is not here yet? So Xingyang, who devoted literally 5 years of his life probably working on neural deep retrieval, can be summarized in the following slides. You take the user, model it by a neural network. You take the item and you put it as a neural network. And you put a softmax on top. Yes, sometimes we use the dot product, or we call it MIPS in the previous talk, maximal inner dot product. Why do we use dot product? Because you do the dot product and you divide it by the partition function. Okay. Now, the partition function is really important because it's negative sampling. We already lied a little bit of that discussion, but basically this is all there is to it. Now, everything is now and then about how do you correct this partition function. If you do it correctly, you get the right data from the user. You do it correctly, you build the best neural deep retrieval model in the world. We've done this at Google. Made Google lots and lots of it. Right? This U goes there, this V goes there, and then you have your softmax. What's about to happen in the field, in my opinion, is that this is all going to go away. How are we going to do it? You already know the answer. We're going to use sequence-to-sequence learning. What we're going to do, instead of the left-hand side, where we use a neural deep retrieval model, a two-power model, we're now going to generate multiple tokens to represent a single item. I should emphasize at this point that it has been wonderful work with the YouTube team, particularly V-Way, Lexi, and people who might not necessarily be here, Khushhall, who really struggled with us for multiple years to figure this out. But we have now started using Semantic ID in production at Google for generating recommendations, and it's working. Not only is it working, it generalizes a lot better. We haven't yet published the full paper on this yet, so I can't tell you all the details behind it. But what I can tell you is that it requires somewhere between 1,000 to 10,000 less data points to get similar or better performance than what we have in production for many, many years inside of Google. Now, literally, this is what we're feeding into the system now. It literally says something like, a 35-year-old male user is watching this video, which is represented by this set of semantic ID tokens. And the title of this video is this, and if you're using this device to watch it, what would you recommend next? That's literally what we do through a transformer architecture. Now, what are these semantic IDs? It turns out we have been very stupid about how we do this for a very long time. Why? Because it turns out that the people who are working on video understanding, image understanding, audio understanding, speech understanding, have all been going down this route for multiple years already. All we needed to do, again, is to adopt their approach. And that was using residual vector computation. I'm not going to go into the detail of how that's done. You can read it in the literature. But basically, it's looking at the pattern in the data and making a decision about how to come up with token representation such that you represent all the items in your category in a particular way. Once you do that, order falls out of the representation automatically. Absolutely incredible how it works. And then multiple tokens decode to a single video, for example. So a token might represent loosely the topic of sports, and then maybe within sports, another token added to it would represent volleyball. As an extension of this, there might be a token that represents Italy, another token that represents East Italy, another token that might represent Bari, another token that might represent sports teams or beaches or whatever. And combined together, that might go to 160. Just the same way that videos are represented. 64 tokens, 256 tokens represent a single video frame. Same idea, using the same exact encoding technique. Our results, which were published in NeurIPS 2013, were very, very good. So in blue, we have the dual encoder approach, the two-tower approach. In yellow was on the Amazon dataset that we were able to publish and show the result of. Much better generalization capabilities. Very importantly, the model itself has 400x more dense parameters. What does this mean? Unlike the actions speak louder than words paper, where most of the parameters are still spent in token representation. Okay? In embedding, we reverse the process. Now the tokens themselves are measured in millions, and the model itself is measured in billions. The model parameter itself is measured in billions. I hope you intuitively understand what's going on, right? Think about it. All of human language is represented by roughly 200,000 tokens, word piece tokens, to be precise, and represent all the different things we could say in sequence form. Yeah, only 200,000. Think about all the different things that we can do with it. You know, again, only 256 tokens represent a single video frame, which could be lots of different scenes, and could be beaches, could be sky, could be a person, could be a robot, it could be a car. 256 tokens represent all the complexity. That's the world that we're going to. That we're going to do this kind of representation. Okay. All right. I feel like I've been talking a mile a minute, so I'm going to take a brief break because the first story is literally the most important part of it, and that took me 30 minutes or so to finish. The next part is going to go by in a blur. So I'm going to take a quick break. Because the reason I wanted to take a break is not only do I think the current way we're building these ranking functions is going to change by this semantic ID technology, generative retrieval technology, which you're probably already poised to believe in when you come into this conference. A greater danger lies in front of us as a conference, in fact. It's not just the fact that we're going to be building these ranking functions differently. Okay? What's coming is the universal system. The reason why we build ranked lists, as I mentioned, was because we process information sequentially, one at a time. You want to consider this? You go to a shop. They say, you want this bag? You want this pair of shoes? I just bought this nice pair of new shoes, right? They give you it one at a time. And the reason is because you're processing the information visually, using a phone, using a computer. Right? But what if it's now in your ears, displayed in your eyes, all at the same time? What would that world look like? I just mentioned that the order and the structure of the entire internet market, $300 to $500 billion worth of it, is determined by these ranking functions. Right? What if all that were to change? What if all that were to change within the next 7 to 8 years? I hope some of you have had a chance. Let me see. It was working before. Try again.
Yeah, you just slide it.
How do I turn it on?
Yeah, just slide it. Yeah.
When you see something that makes sound, I see a speaker which makes sound. What is that part of the speaker called? That is the computer. It produces high frequency sounds. You need to create alliteration about these. Creative crayons color-quickly. This is what we call colorful criticisms. What does that part of code do? This code defines encryption and decryption functions. It seems to use AES-ABC encryption to encode and decode data based on key and an initialization vector, ID. That's right. What neighborhood do you say that in? This appears to be the cost area of London. It is known for its rail station and transportation connections. Do you remember where you saw my glasses? Yes, I do. Your glasses were on the desk near a red apple. What can I add here to make the system faster? Adding caches to the server and database can improve speed. What does this really look like? Scrubbing your cat. Alright, give me a band name for this.
That is a live demo. In fact, I'm not allowed to show it, but it's running in my pocket right now. On this phone. I'm supposed to be guarded with my life. If the universal assistant is right around the corner, as we just showed in this video, and you can walk into any physical store and get help on the product that you're looking at. What prices are available on the internet? And what other options should I consider? Derek, who's very into golf, will be able to buy the best golf club for himself because there will be a shopping assistant that he's carrying in his pocket. And then what would recommender systems be? Would it just be a ranking function? Would I be constantly speaking query terms to my universal assistant? No, I'd be using natural language to talk to it, just like a shopkeeper would, right? And instead of needing to type in tailor-made G10 golf club or whatever and spelling it correctly, I just use my glasses. I'm looking at it and say, hey, is there a cheaper version of this that I can consider on the internet? That's a recommendation action. Possible. How would ads be different at that point in time? If ads is not attached to a ranked list anymore, would there be multiple shopkeepers competing for my attention? Bidding for my attention? Would Titleist, as another equipment manufacturer, now jump in? Or would Etsy jump in and say, by the way, you might want to consider a used version of the club that you're looking at, because you can save $200? Would Etsy be an agent? What would happen in the world that we're about to step into? Make the right investment now, your career will explode, and you will be a multi-millionaire. Almost certain. Right? If you think about what has happened over the last 15 years, you have made the right investment at the right time. Things would be very different for you, and things would be very different going forward. So what are some of the things that I believe are going to be needed? Well, as you can see, we're very hard at work in thinking about multi-step complexities, right? So you should be able to, this is what a recommender system should be able to do now. If I am a 2-year-old golfer, I'm not very good with my driver, which one should I consider? I'm going to Italy, I want to dress like an Italian. What shoes should I bring? That's what a recommender system should do. That's not what the recommender systems currently do. Right? It should know about my preferences, the color preferences that I have because of my skin tone. It should be personalized. It should have full-blown multi-modality input. Take a picture of my shoes and say, what shirts would go along with this? That's a recommender system as well. Right? How are we going to be able to build all this will need a dramatic change in the things that we're investing in. I have a small proposal to the steering committee, even though they might not be here. I have a small proposal. I think maybe RecSys in the future should be called decision support systems. Or even universal assistant research. I don't know, but you get my point. Right? We're not going to be building just a ranked list going forward. Thank you very much. Questions, the mic is not working, but I see one hand up here. And then, you know what those things work right now. I should have brought enough stickers for the question askers.
So thank you all for the talk. It was very interesting. I was wondering, I was really impressed how they were on semantic IDs and on the recommendation that you were from DeepMind. I was wondering if you tried with other inputs during the conversation then to create the IDs, because in my head, the next step would be to change the non-various semantics. I wonder what happens if I get that recreate vision model. Do I get the hierarchy on the IDs?
I hope I got your question correctly, but roughly you're sort of saying, what if I start to change even more of the input, not just thinking about semantic IDs, right? Because we have semantic IDs right now mixing with language as input, and then the output is merely semantic IDs, right? But going forward, once recommendation participates in the whole transformer architecture, the transducer, as a full-blown member of one of the modalities, you can imagine that you can treat it in any sort of form that you want it. So for example, there's no reason why the input has to be text. It could be speech, or it could be an image, right? I could take a picture of a pair of shoes and say, what would you recommend? And without needing to first recognize what kind of shoe it is in text. Like that's basketball shoes, or that's a fashionable pair of leather sports shoes. Doesn't need to know any of that. It's already full-blown native multimodal, right? So if I show it a watch, it will know it's a digital watch and not a Rolex. It just knows without needing to do additional recognition step. That's the world that we're moving to. So your question is spot on, right? So think about how recommender systems should change as a result of that.
Thank you so much.
I think you now believe me that it's a paradigm shift.
Another question.
And there's one down here in the lady.
Thank you very much for the inspiring talk. I'd like to ask what's your take on Jan LeConte's argument that you need a completely different architecture for AGI-like systems and what we've been adding until now?
Yeah, what's going on right now in terms of the architecture that we're limited by is completely by compute. Everything, the way that we're building it, is all because of compute. Now, the reason why we have not been able to serve this at industrial strength, large scale, is purely because of compute. There are some very new ideas that are coming out about how do we save not just 10% of the compute, not just 50% of the compute, but thinking about being able to serve these models at 1% or even smaller amount of the compute. Now, how that's going to happen is actually, in my personal opinion, the potential of going back to more R&D to our lives. Yeah, there was one lady in the hat, in the straw hat. Very stylish hat.
Very much ignorant in my question. I read a kind of paper we are doing now. How can you let the trade which naturally in the interaction in the space will meet together?
How do you map the query into a similar semantic space? Is that what you?
Query the link which is one from the language
Yeah, so the original sequence-to-sequence paper, that was in fact one of the innovations behind the whole paper, was that no matter how long the sequence is, you use an LSTM, you embed it into only one embedding vector, which we, at the time we call it context vector, or in fact Jeff Hinton at the time called it a thought vector. So that thought vector encodes. Don't think about it in terms of similarity, because when you think about it in terms of similarity, you're back to the dual encoding maximum inner dot product world again. That encoding, that context vector, thought vector, encodes ways to decode something. It's a decoding process. It is true that the first decoding uses softmax, which is the dot product. But the next one is a conditional probability based upon the previous token that you just generated, and so on and so forth. So it generates a sequence. So that thought vector encodes various different ways you can decode fault or decode semantics. Okay? So don't think about it in terms of similarity alone. There's one down here.
Okay.
And then just while you're walking, I'll just keep commenting on. There are a lot of great tutorial information out there about sequence-to-sequence learning on the internet.
Thank you for the talk, for this as well. So, what would this model optimize? Ideally, we would like to have some kind of single objective, but it could be like lots of recommended systems currently are multi-objective and stuff. So, and the human could be considered like a single objective system. So, what would you maximize?
That's a very good question. So the question was, what's the objective that you would be maximizing? What's currently happening in large foundation models in terms of how they make decisions is not fully well known. It's, for example, how does it end up optimizing for a summarized document that, or how when you ask for a poem, how does it generate a reasonably good poem? That's why we have a lot of eval. One of my contributions in the initial launch of R was in fact defining the benchmarks and tuning the LM toward that direction. Now, how do we tune it? Post-training. Supervised fine-tuning, RLHF, and now there's a bunch of new techniques on RLMF, RLEF, RLIFF, instruction fine-tuning feedback, even synthetic data generation. So this is all happening within the last year. Lots of different ways to tune these models. Within my team, in Lee Chan's team, and in Derek's team, we're working quite a bit on figuring out how to tune these transformer models so that they beat current production models. And we've done that work with people in Lee Wei's team and in Lexi's team already, and it is proliferating across the YouTube search and YouTube shorts as well. So it's definitely
Well, I think we have time for one.
just a follow-up.
Just to follow up, so recommended systems are kind of different from NLP in the sense that you have like long-term rewards and stuff. So I know you also done like lots of paper on RecSys. So could it be like it's much harder in RecSys to do the same stuff instead of continuing?
That's a great question. So RL feedback to make recommendations over a long period of time, maybe over a whole day or even a couple hours, or diversity problems. How do you get these transformer models to generate diversity? Currently, they're done via instructions and instruction fine-tuning, prompt tuning. But you can imagine that I can already, in fact, your question was perfect because I can already predict 2 years from now, 3 years from now, there will be paper at this conference on exactly the question you asked. In fact, maybe written by you, right? So that's the whole point. Let me use that as an opportunity to summarize my talk. What you want to think about is predict the future, what's going to happen in the field, and then write papers about that. Don't write the incremental paper. I just give you a whole formula for writing non-incremental papers for this conference. And those papers are the ones that are going to be cited in the future. All right? Thank you very much.
Yeah. Just an applause, but I think we can give one more round of applause.
The panel.